Hello, I'm Andrea Iacovo from the Roma University, and today I will present our work about the realization of wavelength selective colloidal quantum dot photodetectors and their employment for spectral analysis. This work has been realized in collaboration with the NANOTEC Institute of the Italian National Research Council. I will start with a brief introduction about colloidal quantum dots and photodetectors. Next, I will move to device fabrication and characterization, and I will describe our approach for the design of a spectral analysis system employing multiple colloidal quantum dot-based photodetectors. Colloidal quantum dots are semiconductor nanoparticles dispersed in solution. These materials were widely studied in the last 2 decades and are now considered a promising platform for the fabrication of several different electronic devices, such as photodetectors, solar cells, LEDs, and chemical sensors. The most peculiar characteristic of quantum dots is their strong quantum confinement effect, which makes the optical and electronic properties of the nanocrystals strongly dependent on their size. So, changing the size of the quantum dots, it is possible to modulate their energy structure, thus changing, for example, their optical absorption cutoff wavelength. Another really nice characteristic of the quantum dots is that they can be easily synthesized in solution with a solvothermal approach. This means that the fabrication costs are really low and that the material properties can be engineered operating on simple processing parameters such as the solution temperature and the reaction time. The outcome of the synthesis is a monodispersed solution of semiconductor nanocrystals, which can be directly employed for the fabrication of thin solid films on a variety of substrates. Moreover, after the synthesis, the electronic and optical characteristics of the quantum dot can be further modified via surface chemistry. One of the most common materials for the fabrication of photodetectors based on colloidal quantum dots is the lead sulfide. This material is best suited for operation in the visible and shortwave infrared range, with optical cutoff wavelength that can be extended up to 2.3 microns. Several different kinds of photodetectors can be realized with colloidal quantum dots, but we focused in particular on the fabrication of simple photoconductors. The devices were fabricated with a layer-by-layer approach by spin-coating the colloidal quantum dot solution onto pre-patterned interdigitated gold electrodes on silicon dioxide substrates. After deposition, the quantum dots were chemically treated with tetrabutylammonium iodide for an in situ ligand exchange. This procedure is mandatory to reduce the distance between the nanoparticles, thus lowering the overall film resistivity and allowing for efficient extraction of the photo-generated carriers. We employed 7 different solutions of monodispersed lead sulfide colloidal quantum dots, with size ranging from 2 to 5 nanometers. The figure shows the normalized absorbencies of the 7 solutions. All the spectra show an excitonic absorption peak and a high absorption shoulder at lower wavelengths, with a typical low-pass behavior. The excitonic peak wavelength ranges from 724 nanometers to almost 1400 nanometers. As expected from a photoconductor, the devices showed a linear current voltage characteristic and a responsivity that is strongly dependent on the applied voltage. Photoconductive gain can also be observed from the responsivity versus voltage graphs. This gain can be attributed to the difference between transit time and lifetime of the photo-generated carriers. As already observed in previous studies, the high photoconductive gain depends on the presence of deep trap states for electrons that dramatically enhance the carrier's lifetime. This is also demonstrated by the gain dependence on the optical power. As shown in the figure on the left, we observed a very high gain at low power, while the gain almost vanishes when the impinging power reaches the microwatt range. This is probably due to the filling dynamics of the electron traps. At low power, almost all the photo-generated electrons are trapped and can participate in the gain mechanism. At higher powers, all the available trap states are easily filled, and a higher number of photo-generated electrons are swept across the device faster than their conjugated whole, thus not being able to trigger any gain effect. We also observed a strong dependence of the responsivity and of the device dark current on the spacing between the metal contacts. This is an expected behavior and allowed us to identify a trade-off between dark current and responsivity. In particular, we opted for 2 micron spaced devices. At this point, I only showed simple quantum dot-based photodetectors, but in order to develop a spectral analysis system, we needed a spectral selective device with a bandpass-like responsivity. To achieve these results, we realized passive quantum dot filters on top of the photodetectors by drop-casting different colloidal quantum dot solutions onto glass substrates that were previously glued on the detector's surface. Such filter layers don't need to be conductive at all, so we could skip the ligand exchange procedure. The filter layer and the active layer can be realized either with different type of nanocrystals or with the same quantum dot dispersion. In fact, thanks to the ligand exchange procedure, the responsivity spectrum of the photodetectors is slightly redshifted with respect to the absorption spectrum of the pristine quantum dot dispersion. Thus, devices where the filter layer and the active layer are realized with the same quantum dots show a sharp bandpass-like responsivity spectrum. For example, here you can observe the responsivity spectrum of an unfiltered photodetector realized with 3.2 nanometers quantum dot. In the center, it is showed the absorption spectrum of the same quantum dot solution, and on the right you can see the responsivity of the resulting filtered device with a full width at a half maximum of only 100 nanometers. So, employing different combinations of filter and active layers, we could obtain several bandpass-like responsivity spectra. Here you can see a subset of such spectra evenly distributed between 0.9 microns and 1.5 microns. Typically, the higher the peak wavelength, the wider the obtained spectrum. So starting from 7 quantum dot solutions, we obtained 28 different devices, each one with a unique responsivity spectrum. Such devices can be effectively employed for the realization of a spectral analysis system. The proposed system is actually quite simple. Imagine that we have a light source evenly illuminating all the 28 devices. Each device will generate a photocurrent that depends on the product between the spectral responsivity of the photodetector and the power spectrum of the impinging optical radiation. This leads us to a system of equations where I is the vector of the 28 photocurrent, R is the matrix of the spectral responsivity, and P is a vector representing the power spectrum of the light source. At this point, a suitable calibration routine and a tuning algorithm can be employed to reconstruct the light power spectrum from a measurement of the photocurrent vector. In principle, the power spectrum could be calculated by solving the linear system represented by this formula. However, the inversion of the R matrix is non-trivial since the matrix is a non-square matrix with a low rank. However, a simple algorithm can be employed to obtain an approximated solution of the equation system. First, we can define an R prime vector obtained as the linear combination of the R matrix rows. This vector represents the spectral responsivity of an ideal photodetector. The weight vector W can be calculated by least mean square fitting. We calculated several W vectors in order to obtain different R prime responsivities with a Gaussian shape and a 10 nanometer full width at half maximum. Multiplying each W vector by the photocurrent vector, we could calculate the amount of optical power in a very small wavelength range, thus obtaining a system that can actually operate as a coarse spectrometer. In order to verify the functionality of the spectral analysis system, we simulated its behavior as a wavelength measurement device. Here you can see the result of the measurement of the peak wavelength of a simulated quasi-monochromatic light source in the wavelength range between 400 nanometers and 1600 nanometers. As you can see from the picture on the left, the system successfully identifies the peak wavelength with a mean 0.3% error. The error becomes larger if the light is less monochromatic and if we reduce the number of spectrally selective devices employed for the calculation. Finally, we simulated the behavior of the proposed system for the spectral analysis of an arbitrary light spectrum. Depending on the spectrum's characteristic, we obtained a mean error between 1% and 3% with a spectral resolution of 30 nanometers. We obtained similar results, also employing a lower number of photodetectors, with the error being less than 3%, even with only 15 photoconductors. At this time, however, these results come only from numerical simulations. We are still working on an experimental demonstration of the spectral analysis system, since we need to develop an optical system that allows to illuminate all the different photodetectors with the same exact optical power and spectrum. This means that we need a custom-made optical system with very low chromatic dispersion. In conclusion, we realized several different colloidal quantum dot-based photodetectors with spectrally selective responsivity characteristics. In particular, we exploited the redshift of the quantum dot's absorption spectrum due to ligand exchange to obtain narrow responsivity spectra in the shortwave infrared range. We proposed the employment of our detectors in a spectral analysis system, and finally, we discussed the characteristics of such system, simulating its response to both quasi-monochromatic radiation and wide arbitrary spectra. Thank you very much for your attention.